Good morning, students. Mr. Carver here. Today we're going to continue on in section 1.3, additional day in 1.3, and we're going to continue to evaluate limits analytically. So for the homework, you actually were finding limits where there was no hole, right? So you could actually just plug in the value of c to find the limit. Today I'm going to be giving you problems where there is a hole, but instead of building a table to find the limit, you're actually going to be using some algebraic tricks to find the limit, and that's what I'm going to be teaching you today. Nothing more than just a series of tricks to be able to determine the limit at a point where the graph does not exist. And here's our first example. The very first thing I would like you to try to do is plug in the value of c and see what you get. When I plug in 3 first here, what I end up with is 0, that is 3 minus 3, over, what is that, 9 minus 6 minus 3, over 0. So let's go ahead and put this in your notes. The first two things I would like you to do is plug in the value of c wherever you see an x. And then I think I mentioned this yesterday in class, but I want you to beware of 0 over 0. 0 over 0 is this thing called indeterminate form. Good morning. And that means that you can determine nothing. You've got to explore more. You must do more work. And I'm going to show you what that work is today. Again, those are nothing more than the algebraic tricks. So the majority of problems you are going to get today are going to result in 0 over 0. And then you'll follow it up by doing what I'm going to teach you to do right now. So 0 over 0 is the thing you got to watch out for. Let me clear this up, and then let's work this problem. So one of the techniques that you're going to use today is just factoring. Factoring and canceling. So if you recall, I think we actually worked through this in class the other day. The bottom factors to x minus 3. What is that? X plus 1. I can now cancel that. And now what I'm going to do is I'm going to take the limit as x approaches 3 of 1 over x plus 1, and I'm going to try it again. Now if I plug in 3, what I get is 1 over 4. That is not 0 over 0 any longer, and that actually is the limit. Now, we did talk about this in class yesterday. This function right there and this function right there, if you were to graph them, they look exactly the same, except the one on the left has a hole at x equals 3, and this one has no hole anywhere, especially at x equals 3, which allows you then to just plug in that number, 3, and get an answer. So that's the first technique for today. The next technique is going to look something like this. Say I take the limit as x approaches 0 of 1 all over x plus 4 minus 1/4, and that's all over x. All right, now this is a complex fraction, and that is fractions within fractions. So again, I'm going to make this really dark right here because that's my main division bar. It's all of the top divided by the bottom. I'm also going to make the bottom into a fraction. Now, if I take the top fraction, divide it by the bottom fraction, recall that you have to copy dot flop. That's the way that you divide fractions. But before I copy dot flop, I've got to clean up the top into a single fraction. So what I'm going to do is get a common denominator here. I'm going to multiply the first one by 4 on the top and bottom, and I'm going to multiply the second one by x plus 4. on the top and the bottom so that the denominators match. So here's what I'm going to get. On the top, I get a common denominator of 4 times x plus 4. And on the top, I'm going to get 4 times 1 minus 1 times x plus 4. So when I combine it, I get a common denominator. I combine it into a single fraction. The expression on the left turns into the expression on the right. Now, I still have my big main fraction bar, and this is still over x over 1. So I've not divided the two fractions yet, but I'm getting close. So what I want to do now is I want to clean up this big fraction right here. So if I simplify the top, what I'm going to get is 4 minus x minus 4 all over 4 times x plus 4. Again, this is still all over x over 1. And then what you'll notice here is that the 4 take away 4, these just go away. And I end up with negative x on the top of 4 and x plus 4. And now what I'm going to do is copy dot flop this fraction on the bottom. When I flop that, I get a 1 on the top and I get an x on the bottom. So on this bottom row here, the 1 on the left is turned into the 1 on the right. Now I want to take the limit as x goes to 0. And what you'll notice here is I still get 0 over 0. And let me back up here just a little bit. I know I always said plug in 0 first. I did skip that step. Well, I didn't skip it mentally, but I skipped it verbally. If you plug in a 0 here, I get 1/4 minus a 4th on the top, which is 0. And I get 0 over 1 in the denominator. So it was indeterminate, which then necessitates the rest of this process. Now, even though I've eliminated the complex part of the fraction, I've combined it into a single fraction, this part right here, it is still indeterminate. So now what I want to do is I want to cancel these x's. So I'm going to cancel this x here with this x here. That leaves me a negative 1 on the top, and on the bottom I get 4 times x plus 4. And now I can try it again. I take the limit as x goes to 0. I get a negative 1 on the top, and I get a 16 on the bottom, which is not 0 over 0, and that is my limit. So I go from indeterminate form into determinate form by using this process of common denominators, copy dot flopping, and canceling. That's another type of problem that you're going to see tonight. All right, let's do another example. How about this one here? Now, delta x looks like two different types of variables, but it's actually just one. Think of it as a single variable. So if you'd like, you could turn this whole thing into a single letter, like h if you'd like, or just use delta x. Either way works. All right, now the first thing I do is plug in 0 for delta x. And won't that give me, then on the top, x squared minus x squared all over 0, which is the same as 0 over 0, which is indeterminate form. So what I'm going to do now is just simplify this and see if I can get things to cancel. So if I FOIL out this portion right here, using the box or FOIL method, what I'm going to get is x squared plus 2x delta x plus delta x squared minus then the other x squared I still have on the top. And this is all over delta x. Now keep in mind, I am still taking the limit as delta x goes to 0. And what I want to do now is just clean up the top. And what you'll notice here is that this x squared and this x squared cancel. And that looks like just about it. So now I've got 2x delta x plus delta x squared all over delta x, taking the limit as delta x goes to 0. Now if I plug in 0 for delta x, I get 0 on top and 0 on the bottom, so it is still indeterminate. So now what we want to do is try to factor and cancel. I think you guys would agree that I can pull out a delta x at the top, leaving me a 2x and 1 delta x here. And by the way, if I distribute this, I get back to where I was before, so I'm okay. This is then all over delta x, And what you'll notice now is that I can cancel those delta x's. And now the last thing I want to do is take delta x and replace it with the value of c, which ends up giving me 2x plus 0. And that is my limit. I know it seems weird not to have a numeric limit, but it will happen occasionally in tonight's homework. That is what you're looking for. All right, let's do another example. What if I said, let's take the limit as x goes to 0 of the square root of 2 plus x minus the square root of 2 all over x. Now, if I plug in 0 for x, what I get on the top is root 2 plus 0 minus square root of 2 all over 0, which is the same as 0 over 0, which is indeterminate. Badness. So let me show you how to get rid of this. What you're going to do, if you've got an expression with radicals, I should say a sum or difference of a radical, either in the top or in the bottom, here's the way you're going to handle it. You're going to multiply by the conjugate. And the conjugate is the same things. So you've got root 2 plus x and a root 2, but the sign in between them is different. So this becomes a plus. And you want to do the same thing on the top and the bottom, because as you're working on limits, whatever you do to the top, you must do exactly the same thing to the bottom, otherwise you've screwed it up. All right, now if I take the top, remember when you're multiplying fractions, you just multiply straight across. So if I take all of this, the top, just the top only, and I FOIL this out using the box method, here's what I'm going to get. I get root 2 plus x times root 2 plus x, otherwise known as just 2 plus x. This is going to be plus root 2 times root 2 plus x minus root 2 plus x, and then minus root 4, or just 2, all over x times root 2 plus x plus square root of 2, because again, I just multiply straight across. All right, well, what you'll notice here, as I multiply by the conjugate, this term and this term cancel each other out. I can also see that I've got a 2 and a negative 2, which cancel each other out. And that just leaves me x on top and an x times root 2 plus x plus root 2 on the bottom. Now, if I still take the limit as x goes to 0, I'm still in indeterminate form. But you can cross out those x's. You can cancel them, leaving me a 1 on the top. And what I'm going to do is plug 0 in for x, this x right here. And that's going to leave me root 2 plus 0 plus root 2, which is 1 over 2 square root of 2. Because there's 1 here and there's 1 here. When I add them together, I get 2 of them. This, then, is my limit. All right, so those are the types of things you're going to be doing on tonight's homework. I've got 2 more things to show you. It wouldn't be calculus unless we were doing trigonometry. So here's what I want you to do. I need you to memorize these things. So memorize these 2 formulas. You can use these formulas throughout the rest of the year in this class. And here's one. The limit as x goes to 0 of the sine of x over x, that is always equal to 1. The limit as x goes to 0 of 1 minus the cosine of x all over x is always equal to 0. By the way, it's really important that this go to 0 for these to be true. By the way, if you need convincing as to why these are actually homework problems out of section 1.1, excuse me, 1.2, I believe, when you were actually building tables. Now, just something that's interesting about here, about these 2 formulas, is that the argument and the denominators, as long as they match, the formulas still hold. So let's say I've got something like the limit as x goes to 0 of the sine of 3x over 3x. That limit is still 1. Likewise, with the other one, let's say I take the limit as x goes to 0 of 1 minus the cosine of pi x all over pi x. That is still 0. Also, this first one right here is flippable. So if I take the limit as x goes to 0 of 8x over the sine of 8x, that is also equal to 1. The second one is not flippable, but the sine of x is. All right, so let me show you how to deal with this. Let's say you've got a problem that looks something like this. The limit as x goes to 0 of the sine of 3x, but let's say it doesn't match. Let's put like 5x on the bottom. All right, now when you plug in 0, I get the sine of 0, which is 0, over 5 times 0, which is also 0. So that's indeterminate form. If you have trig and it's in indeterminate form, what you want to do is begin to split apart this fraction right here. And it's multiplication, so you can split it apart however you like. Let's say I take this then, as x goes to 0. What I'm going to do is split off the 1/5 from the sine of 3x. And that's just x on the bottom. Now I still have 0 over 0 here, but in order to get to this formula here, I need this number right here to be a 3. But I can't just write a 3 in there. I need to multiply top and bottom by 3. So I'm going to multiply that expression all by 3/3. And then what I'm going to do is just put it in a different order. I'm going to move that 3 right here. So this is going to give me the limit as x goes to 0 of 1/5 times the sine of 3x all over 3x. And that's going to leave me 3 over 1 there, because that 3 now moved from underneath the other 3 over to underneath the sine of 3x. Now the nice thing about limits is that you can just take them all individually. The limit as x goes to 0 of 1/5 is just 1/5. The limit of the sine of 3x over 3x is just 1. And that comes straight from the formula on the previous page. The limit, as x goes to 0 of 3 is just 3. And then you just multiply those numbers together, and you end up with 3/5. Now, I know you might be thinking, hey, listen, can I just take that 3 and that 5 and just move it out to the front and just write it like this? 3/5 times the sine of x over x, and the answer is no. If I see that type of work on the test or quiz, I'm going to mark it wrong, and here's why. The sine of 3x is not equal to 3 times the sine of x. This is a stretch of the y. This is a shrink of the x. Those are not the same. So this is the type of work I'm looking for on these types of problems. All right, people. That should be enough to get you through tonight. Guys, I'll see you soon. Email me should you have any questions, and take care.